Hello, my name is Matthew Levesque, and I'm going to be presenting about the ozone layer. The specific question that I'll be talking about is why are there holes appearing at the poles in the ozone layer? To address this question, the first thing that I'll be talking about is just about the atmosphere in general, its components, what ozone does, and give a brief background on all those topics. The atmosphere has many functions for living things on Earth. The first function is to warm the Earth's surface via the greenhouse effect. Another function is to provide oxygen and carbon dioxide for plants and animals. The third function, the most relevant one to this discussion today, is to protect all living things from ultraviolet light that comes from the sun. There are 5 main layers of the atmosphere. The first layer is the troposphere, which is the air that we breathe. It's composed of mainly nitrogen and oxygen. The second is the stratosphere. This is the layer in which ozone is present, and it's very relevant to what we're going to be talking about today. Next are the mesosphere, the thermosphere, and the exosphere. So what is ozone? Ozone is a substance consisting of 3 oxygen molecules with resonance and delocalized electrons between the oxygens. What it does is it absorbs light, UV light, of the wavelength 240 to 320 nanometers, and this has a very important function for all living things on Earth. That function is to prevent this UV light of getting into living organisms, which have DNA. Light of this energy can break bonds within DNA and cause problems such as cancers and mutations. In the late 1970s, however, it was found that, especially in Antarctica, ozone levels were rapidly decreasing. This is shown in this figure. It shows the minimum ozone every year, since ozone levels fluctuate. It shows the decrease between 1979 to 2014. It also shows that the hole in the ozone layer was increasing from 1979 to 2014. The data also showed seasonal fluctuation in ozone levels that were repeated year after year. So as research increased in this area, the first compound that was found to be a significant cause of this were chlorofluorocarbons. Or CFCs for short. What CFCs are a carbon molecule combined with fluorines and chlorines. So what these do is UV light will break the carbon-chlorine bonds on these molecules, and so this is just electrons moving apart. So one electron goes to the chlorine, one electron goes to the carbon. And UV light does this again because it's a bond-breaking energy, so it has sufficient energy to do that. And what we get is chlorine radicals, as well as the rest of the molecule, but those don't play a big role in this issue. The chlorine radicals are extremely important for ozone depletion because they react in a series of events that go on to turn ozone back into oxygen at a very fast rate. So as we move on to the next set of reactions, what we find is that the chlorine radicals act as catalysts. Catalysts are compounds that don't get used up in a reaction. So as we see here is a chlorine radical, and it reacts with the ozone to produce chlorine monoxide and oxygen. Later, the chlorine monoxide that's produced here will combine to form Cl2O2. Following that, that'll break down, produce Cl radicals as well as chlorine radicals again. So you see a chlorine radical is being reproduced from that. And then the last chlorine peroxide radical goes to break into oxygen and chlorine radicals. So as we see, we had 2 chlorine radicals at the beginning of the reaction, and they will be reproduced at the end. So they're not getting used up. They can just keep doing this over and over and over again. All the rest of the reactants cancel out, and we get the overall reaction being 2 ozone molecules are depleted to 3 oxygen molecules. And this happens with chlorine radicals as a catalyst and UV light. So as I mentioned, chlorine radicals can exist in the atmosphere for long periods of time. So how does the atmosphere deal with them? There are 2 major sinks that chlorine radicals or chlorine molecules go to, and these 2 sinks are hydrochloric acid and chlorine nitrate. How this works is that intermediates from the chlorine radical initiation of the breakdown of ozone, chlorine monoxide, which is one of them, react with radicalized hydroxide molecules to make HCl and NO2, and O2, and HO2 radicals, plus chlorine radicals, react to form HCl and O2 as well. That's how the HCl sinks, both these methods are how the HCl sinks are formed. The other major sink of chlorine is the chlorine nitrate. And this happens by the intermediate chlorine monoxide reacting with a NO2 radicalized in the atmosphere, which is always there in some amounts. They react to form chlorine nitrate. And these are the 2 major sinks for chlorine radicals in the atmosphere. Just a quick note, CFCs were used as refrigerants, blowing agents, and solvents. All of its sources are anthropogenic, so they're not produced in nature at all. Since the finding of CFCs, we have also found that other carbon halogen molecules and nitrous oxide are both also ozone depleting substances, and they are produced in the environment as well as anthropogenically. They also react similarly to chlorofluorocarbons, just not to the same extent, but they react by radical mechanisms. So now that we talked about the mechanism of chlorofluorocarbons and other ozone depleting substances, a logical question would be, why does ozone depletion only occur in the poles? Especially when chlorofluorocarbons and all these other ozone depleting substances are only produced in cities and where people live. The main reasons are, as we all know, the poles are extremely cold, but they also have polar vortexes. Polar vortexes are wind patterns that encircle all the poles and keep all the air there isolated. Both of these properties of the atmosphere above the poles allows for the formation of what are called polar stratospheric clouds. Polar stratospheric clouds are when vapors in the atmosphere, in the poles, crystallize and form solid crystals in the air. Polar stratospheric clouds only form during the winter months at the poles because this is the coldest time and they get the least sun. So how they form is, as I talked about before, chlorofluorocarbons had 2 major sinks, hydrochloric acid and chlorine nitrate. What happens is during these really cold months is the vapors of these 2 sinks crystallize out nitric acid. And this nitric acid is in little crystals that make up the polar stratospheric clouds. And while this happens, the 2 chlorines get released as chlorine gas. However, since the winter is very dark, this chlorine doesn't get any UV light and it doesn't break apart. But come spring, the first rays of UV light actually break apart these chlorine molecules, forming chlorine radicals. And what happens during the spring months is the nitric acid is still crystallized from the winter, but the chlorine radicals are out. So that means all the chlorine radicals can react and react and react and react until it starts warming up enough that the polar stratospheric clouds start dissipating. And once they dissipate, eventually we get back to the reactions I mentioned earlier, hydroxide radicals and nitrate radicals reacting and forming the sinks again. This cycle would explain for why you get a lot of seasonal variation in ozone depletion. Specifically, the spring has the lowest levels of ozone nearly every single year. So, since ozone depletion occurs predominantly in the poles, why is this worrisome for us? It shouldn't let UV light get in too much where we live. There are four main reasons why this affects us directly right now. The one reason is that ozone depletion doesn't only occur in the poles. The holes are just the largest there, based on polar stratified clouds and the other reasons we talked about. The next reason is because these holes are expanding. Over the years, the area of the poles, or the holes in the ozone has also been increasing. For this reason, it could start directly affecting northern communities and causing increased rates of cancer, cataracts, and mutations. The third reason is because these chlorine molecules have a very long lifespan. The chlorine radicals in the air, they are not disposed of in the atmosphere. They're stored in sinks, however, they're not gotten rid of. They can last up to 100 years in the atmosphere and convert over, each chlorine radical can convert approximately 100,000 ozone molecules into oxygen. And that's just one chlorine radical. Next, a major concern is small marine microorganisms. It is estimated that if there's a 15% decrease in ozone globally, approximately 50% of the phytoplankton in the sea will die. This is because they are already at their maximum threshold for ultraviolet radiation with the ozone in place. If it continues to decrease and they die, that causes all sorts, it's an ecological disaster. It also, if we want to talk about how it directly affects humans, fish eat plankton, bigger fish eat those fish, and we eat those fish. So it's a chain of events. If the phytoplankton and other marine microorganisms die off, the more fish will die off and we'll have less fish. This is very important because fish make up approximately 30% of the animal protein that humans consume today. So what are we doing about this issue? The main thing that's been accomplished is the Montreal Protocol, which was put forth in 1987. Originally, this protocol phased out chlorofluorocarbons because of their direct impact on the ozone layer. Since then, as more and more substances have been classified as ozone-depleting substances, they have been placed under the protocol as well, and they're being phased out, if not phased out already. So, since the Montreal Protocol was put forth in 1987, ozone levels have been found to not be decreasing. They haven't gotten better. However, this is expected to take a long time because of the long lifespan of chlorine molecules and other radicals that are existing in the ozone layer.